So I'm very honored to introduce Chris Rowan. He is a first-year graduate student working towards his master's in the Department of Earth and Planetary Sciences at Rutgers. And he also got his undergraduate degree from Rutgers. And he will be talking to us today about plate tectonics. And take it away, Chris.
All right, thanks, Lauren. Yeah, so today I'm going to be talking about plate tectonics. And are these tectonic plates dishwasher safe? I would say no. Hopefully, by the end of the talk, I can convince you that these aren't the types of plates that you are putting in your dishwasher, but types of plates that cover the entire Earth. And to get started, just a little bit about me. I'm a graduate student in the Department of Earth and Planetary Sciences, as Lauren said. I'm also a structural geologist, so I study the way the Earth deforms, why mountains form, why continents split apart. And I really like to hike and camp. And my favorite landscape features are probably mountains. I think they're beautiful features. And so to start in on plate tectonics, at its very simplest, the Earth's surface is broken up into these large plates, okay? And these plates move very, very slowly by processes in the deep Earth. And this is a map here, and it's showing the globe, and it's just presented in a flat style. And what I'm going to do here is enlarge that map. And here's North America up here, just to point everything out. And Africa, Eurasia, so here's Europe, Asia, Australia, South America. And what I'm going to do here is just start highlighting some of the plates that cover the globe. So first you have the North American plate here, the South American plate, Eurasia plate, Pacific plate, probably the largest plate, the African plate. And so you can see that the Earth is largely covered by these plates, and some of them are very big and some of them are very small. And to first understand why the plates move and what happens at boundaries, we have to first look at the structure of Earth. And first, a lot of us are familiar with the crust, so that's this top region here of Earth, this dark brown here. And this is about 0 to 100 kilometers thick. And this diagram here, it's not to scale, but if we look over here, this little slice of Earth here, this is to scale. And what you have here, this little black line that outlines this half circle, well, that's the crust to scale. And it's comparable to a skin on the apple. So as you can see, the crust, what we live on, is really just very, very small in comparison to the full size of Earth. And then if we go a little bit deeper in Earth, we have the mantle. So that's this region here, these shades of orange into this tan. And that would be the second layer down. And that would be this orange layer here on this diagram. And if we go a little bit deeper, we hit the core. Okay, a lot of people are familiar. The core has an inner core and an outer core, and that's what makes our magnetic field. But to first, to understand what we're going to be talking about today and plates, we're only going to be looking at this top region here of Earth. And so to zoom in on that region, we have to divide the Earth a little bit differently than just the standard crust, mantle, core. And in terms of what the plates are actually made of, well, that's the lithosphere, which means it's a rocky sphere. And that's the crust, so the uppermost crust here. And then part of the uppermost mantle, which is solid. So this region, the lithosphere, is made of rock, and it's rigid, and it's hard. And underneath that is the asthenosphere, which is a weak sphere. And that's made up of the upper mantle. And this is solid, but it's capable of flowing. So you can think of it like Jell-O. Jell-O, yes, it's a solid, but if you shake the table or move it around, it's capable of flowing left and right, just like putty as well. And so the key is that these lithospheric plates okay, the lithosphere, floats on the asthenosphere due to differences in the property of the solid, whether that solid is rigid and hard, or it's putty-like and it's capable of flowing. And so what drives plate tectonics? Well, convection currents cause plates to move, and specifically convection within the asthenosphere. And this is kind of analogous to a boiling pot of water. And so here in this diagram, we have a heat source. So here's our flame. So just think about putting a pot of water on the stove, and we turn on the stove and we have a heat source down below, and that's heating the bottom of the pan here, or the pot. And what it's doing is heating the water, and as that water heats, it slowly rises and then slowly cools, and it circulates, and it makes these large convection currents. So what it does in the Earth is it carries the heat from the center of the Earth's core to the surface. And just remember, the same thing happens within a boiling pot of water. It's all the same. So if we step back and look at a slice of Earth and look at what's driving plate motion, well, it's convection currents and something called slab pool. And so let me explain what's going on here. So here's our slice of Earth. We take Earth and we cut it down the middle, and we see we have our crust, our mantle, and our core. And remember that heat is being produced within the core itself. And what you have is in the asthenosphere, in the mantle, you have convection currents. And so it's the heat being produced in the core is causing rock to rise in the Earth and move towards the surface. And then as it moves up, it slowly cools and comes over and starts going down. So here's our convection current, just like in a pot of water. And something important to point out is that here are our plates right here. So here's one plate, and here's another plate. And there's actually two little plates off to the side here. So we see 4 plates. But what's important is that the heat is rising and basically pushing up here on what we're going to call a ridge, and I'll get into this in a few minutes. And it's causing these plates to move away from this area where the heat is rising. And then, as you can imagine, as this plate moves along here, eventually it's really hot initially here, it's going to cool, it's going to get really cold and dense, and eventually as it starts to sink into Earth, when it comes into contact with another plate, you can think of this is called slab pull. The actual weight of the slab itself is pulling this plate down into the Earth. And so this is really the dominant force, slab pull. And you can think of that almost like if you're sitting on the side of a boat and somebody just ties a weight around your ankle and drops it in the water, you're also going to go down into the water as well. So it's a cold, dense, thick slab which is getting pulled down into the mantle. And so as these plates move all around the globe, what happens when plates encounter each other? And well, for that, we have plate boundaries. And so there's 3 main types of plate boundaries: convergent boundaries, where 2 plates are coming together, and that usually creates mountains or some kind of high topographic feature. Divergent plate boundaries, where the crust is splitting apart, it's diverging because there's some kind of upwelling or heat which is pushing up and making the Earth split apart. And there's also transform plate boundaries, where the Earth is just sliding past each other. It's not so much gliding, but sliding. So you can think of these processes here as processes that will build or create new continents or features. And with transform, it's really just 2 plates sliding past each other. And so the plate interactions at boundaries really creates the topography we see on Earth. So the mountains, the valleys, are all created by the movement of plates, by plate tectonics. And so let's go exploring. Where do these features occur? Well, here's a map of the world here. And And what you see, it's colored a little bit differently than you're probably used to seeing. And again, we take a sphere and we have to kind of lay it out so the Earth is flat and we can view it in 2D. And what you see here, all this blue area, well, these are the oceans, right? The Atlantic Ocean, Pacific Ocean. And what you see is these are our continents. So here's North America. And this is called a digital elevation map. So it's showing the elevation. As you can see, the Rockies are very tall. So they're kind of this dark brown. Down here in South America, here's another mountain chain, as well as the Himalayas. Everybody is familiar with Mount Everest. That's over here. So the darker the color, more towards brown and white, you're going to have higher elevation. Whereas in somewhere like here where it's green, it's not that high of elevation. And of course, our oceans are blue. So as I start to point these out, look at what are the topographic features that are at these plate boundaries. And first, let's ask ourselves, where do convergent boundaries occur? And well, that's, like I said, the Himalayas here. So we have two plates moving together. So here's India, the Indian plate, and here is Eurasia. And basically India collided here and formed the Himalayas. And then also here in South America, you have the Andes Mountains. And basically South America is moving, and here comes the Pacific plate, and it's going underneath and kind of pushing up a mountain range. And so these are convergent boundaries. Well, how about divergent boundaries, where plates are pulling apart, where they're actively breaking apart, we're creating new new oceanic crust, new crust. And so that would be something like a mid-ocean ridge. So here, I can trace this with my cursor. You see there's kind of a line where it's a little bit lighter of a blue here. Well, this is the mid-Atlantic ridge here. And this is where two plates are actually splitting apart, and we're creating new ocean floor all down the Atlantic, as well as we can also break apart a continent, just like East Africa is doing. And here's the East African Rift Valley. And notice here, because I'll come back to this later in the talk, but this landscape is dotted by these lakes. And we'll take a look at that later when we're looking at paleogeography. And so how about transform boundaries where plates are sliding past each other? Well, I think the best example of that is the San Andreas Fault in California, where it causes massive earthquakes. And so we have to talk about plates and rates. So the rate that they move, and plates move very, very slowly, okay, 2 to 5 centimeters per year, which is comparable to the rate your fingernails grow. And so given enough time, plates moving very slowly can form supercontinents like Pangaea. And so what I'm going to do here in the next few slides is take you through the configuration of the continents and the movement of the continents through the past 600 million years. And so here we are. This is our present day continental distribution. And before I explain the map here, let me show you what's going on down here. And so this bar down here, this is going to be our time scale. Okay, so red, we're all the way filled in. We're at present day. Okay, and what you're going to see in the next few slides is this bar is going to start chipping back as I click through, and you're going to see the continents move as well as time moving backwards. And so let's just orient ourselves where we are. Here's North America, right? Here's New Jersey, somewhere around here. South America, Africa, Eurasia, India, Australia, Antarctica, okay? And now I'm gonna step back through time to the Pleistocene, not that long ago, maybe 2 million years ago, this snapshot is here. And what you can see is that largely the continents are in the same place. However, we have large ice masses. Here, all this white, these are large continental glaciers. This is the ice age that you're looking at here. I'm gonna step back 20 million years ago. Continents are still in roughly the same position. But as I start stepping back 50 million years ago, things start to change. And here's the 65 million years ago, the KP boundary, the extinction of the dinosaurs. As you see, we're stepping back through time, so the Atlantic Ocean is slowly closing. 90 million, 105, 120, 150, 170, 200. Look at the Atlantic Ocean now. It's just a little strip here. And so as you see, the continents move through time because of these different currents and these forces to pull plates around and move them. They're going to distribute themselves. And so the same distribution of continents we have today is not the same as we had in the past because these continents move. Here's 430 million years ago, 470, 500 million, 540, 560, and eventually 600 million years ago. And we look at this, and it does not look like the Earth that we are familiar with today. It's brown, and we have polar ice down here at the South Pole, but it looks very different. The continents are not in the same position as they are today. And so now let's go forward in time. Let's go from 600 million years ago to the present. Maybe this will make a little bit more sense to us. Now we're not going backwards, but we're starting at 600 million and moving forward through time. And so here we are in the late Proterozoic, 600 million years ago. And as we go forward, 560, the early Cambrian, 540, the late Cambrian, so around 520 million years ago, we had something called the Cambrian explosion. And you see here, I'm going to start putting up little symbols of things to help us know where we are in time and what's going on. So trilobites and really the first advanced animals start to appear on Earth around this time. And as we go forward, you see again, the continents are slowly moving and slowly drifting together, making mountain ranges when they collide, 430, 400 million years ago. In the late Devonian, we have our first vertebrate ancestors are starting to make their way from the sea onto the land and start crawling and evolving to live a terrestrial life. And as we go forward, now we're still at this point, we're building Pangea. All the continents are coming together to build a supercontinent, Pangea. And finally, we have Pangea. And here we are in the early Triassic, and dinosaurs are starting to evolve and be diversified. And you can see here around 220 million years ago, well, we start to break Pangea apart. And recall back to the East African Rift Valley that was dotted by lakes. The continents are splitting apart. Here we are 220 million years ago, and Pangea is breaking apart. And this is, this goes along saying that the present is the key to the past. So we see features today, and we can relate them to features in the past Earth. And as we step forward in time, you see the Atlantic Ocean really beginning to split apart here. And now the Atlantic is fully open. And here we have flowers. So flower plants evolved in the early Cretaceous. And these are the plants that dominate us today, dominate the landscape today. And as we start to see the modern distribution of continents. It's starting to look a little bit more familiar to us now. And then 65 million years ago, we have an asteroid hit and the extinction of the dinosaurs. And as we come into the Eocene, so 50 million years ago, it's really starting to look like the modern distribution of continents. Mammals are diversifying during this time. And then we get back into the Pleistocene, where we have abundant fossil record of our hominin ancestors at this time, as well as woolly mammoths roaming the continental United States. And so now we are back at our present day. No more ice coming down to latitudes, to areas similar as far down south as New Jersey. And now we're back, and you see that as these continents move over the globe through time, it creates different land masses and different mountain ranges, and those mountain ranges wear away, wear down, and erode. And so why do we care about plate tectonics? Why do we study it? Well, one important reason are geohazards. Um, the distribution of earthquakes is highly correlated to plate boundaries. So there's a lot of earthquakes. You can imagine when you're bumping two plates together, pulling them apart, you're gonna rattle the earth, and that's gonna make an earthquake. And this is very destructive forces. So you can see here an earthquake occurred and there's tons of building damage. So it's really important to understand plate tectonics if we want to be able to predict earthquakes or how to build buildings that can withstand the shaking from these earthquakes, as well as evolution. The movement of plates helps us understand the evolution of plants and animals. And particularly here, what you see is a diagram, and you're seeing a fossil here. So this is some maybe dinosaur or reptile. What you can see is that we find the same fossil on the South American continent and the Africa continent. And it really only makes sense that you would find those same organisms if the configuration of the continents were one big landmass. So it also helps us understand the evolution and the diversification of animals as well. And finally, it's really important to understand tectonics and plate tectonics because of long-term climate. The creation, destruction, and movement of continents and oceans has great influence on long-term climate change. So where high topographic features are can alter atmospheric patterns and can change climate. So it's really, really important to start thinking about plate tectonics through time and how that's really shaping our diverse Earth that we see. And with that, I'm going to transfer over and start answering some of the questions that everybody submitted here. And let me see if I can do that. Okay. I think I'm back to that screen. All right. All right, Mary from Scotch Plains wants to know which is thicker, the ocean crust or crust under glaciers. So the crust under the glaciers, if you recall, well, that's sitting over continental crust, and continental crust is much thicker than ocean crust. Ocean crust is maybe 7 to 9 kilometers thick, where continental crust can be as far as 40 to 100 kilometers thick underneath mountains. So continental crust is much thicker than oceanic crust. Does a ridge like the Mid-Atlantic Ridge divide a plate, or is it part of a plate? And so the Mid-Atlantic Ridge is not divides two plates. So remember, at these ridges, we are creating new oceanic crust, and we're splitting the Earth apart and creating new plates. We're just adding on to these plates pretty much. So it's really the Mid-Atlantic Ridge is dividing plates. Do plates ever just spin on the axis instead of moving northeast, southwest? And so this is a complicated question, right? So first we have to think about having a sphere, and that sphere is broken up into all these plates, and these plates are moving. So if all the plates are moving on a sphere, how do you define the direction which the plates are moving? And the answer to that is, well, you have to keep one fixed. You have to keep one plate fixed on the sphere and then have all the other plates move relative to the stationary plate. And oftentimes it's the Pacific plate or Africa, which is held fixed. So it's really that you're holding one plate constant and the rest are all spinning around or moving around. Okay, I have another question. It looks that we live near the Watchung Mountains in New Jersey. Is there a corresponding mountain chain in North Africa? And to answer that is yes. So our equivalent when the Watchung Mountains are formed during the breakup of Pangaea, during rifting, and what you have is basically our equivalent is in Morocco, in Africa along the coast. So there's a mountain chain there, which is the equivalent of the Watchung Mountains. What were the oldest mountains in North America on the East Coast, and did they form from plate tectonics? So yes, the mountains form basically all mountain ranges. They are products of plate tectonics, and here's an example from right here in our backyard in New Jersey. Are the New Jersey Highlands, just a little bit north of Rutgers, and that's 1.2 billion year old rock, and these are metamorphic sediments. So these are rocks that were buried deep into the crust, maybe 10 or 15 kilometers. And these were during the Ottawan orogeny. So it's this mountain building event happening 1.2 billion years ago. Somebody asked, can a plate just sink into Earth like a sinkhole, or does it always float until it gets pushed under a plate? And this is a good question. So the plates will, for our discussion, the plates will always float, except for when they come into contact with another plate that has a different density. So, for example, continental crust is a lot less dense than oceanic crust, and so if here's our continental crust and here's our dense oceanic crust, when they come into contact, the oceanic crust is going to subduct and go under the continental crust because the difference in density. And somebody asked me to talk about the new plate under Southern Europe and how do science know about it. So I had to look this one up. A Greenland-sized piece of continental crust called separated the North Africa about 240 million years ago and during the Triassic period. But long before humans came, tectonic shift forced the continent of Earth's mantle deep beneath Europe. So basically, there's this old crust underneath Europe, and we can know about it through seismology by basically looking at the way seismic waves travel through Earth. Somebody else asked, how do plates interact with Earth's magnetic field? And this is a very, very good question. It's something I did not bring up during my talk, but is essential to plate tectonics. But as we produce new oceanic crust from ridges, the composition, the rock type of that oceanic crust is basalt. So it's this dark, dense rock. And it has iron elements in it. It has elements that will react with a magnetic field and align to that magnetic field, whether it's oriented to the north or to the south. And so it's almost like these, the basalt that's produced at mid-ocean ridges are basically fingerprinted by the magnetic field. And then somebody else asked to follow up on that question, do magnetic fields ever cause plates to move? And the answer to that is no, but as I said, it does leave a magnetic fingerprint in the basalt itself. Okay, somebody else asked, do new plates have the same chemistry as old plates? And so chemistry of plates is very specific to where the plate is being produced. So for example, if we take our mid-ocean ridge, it's always going to be a basalt. So mid-ocean ridges, the composition is always of the mid-ocean ridge type. So when we're creating new oceanic crust, the chemistry of that mid-ocean ridge is going to be the same type of basalt, essentially. There might be a little bit of difference, but it's going to be essentially the same composition. And so, I just lost my place on the questions. Can earthquakes by themselves make plates? The answer to that is no. But earthquakes occur at plate boundaries. Again, think about plates moving all around the sphere and crashing into each other and bumping up against each other. There's going to be a lot of earthquakes at these boundaries. What determines how many plates are on Earth that Earth has? And so it depends on the way you break up Earth, or if you consider plates broken up. So some people will break up East Africa and say there's two plates there, so the Somalian plate and the African plate. So it depends, but largely there's the number is around 15 to 18 plates. Are there plates on other planets? Well, the answer to that, I'm not really sure. But if we think about Jupiter's icy moon, Europa, there's cryovolcanoes. So there's a form of kind of plate tectonics, but it's not really magma driven or rocks, but it's frozen pieces of ice and volcanoes that kind of explode ice pretty much, as well as recently we've learned there's mini Mars quakes. So maybe Mars is just one big plate, but there are little earthquakes on Mars. And Sarah from, where's my, oh, here we go. Why do mountains form? Well, mountains form because of two continental land masses, or an ocean crust and a continental crust coming together in a convergent boundary. You can think it's pretty simple. Just take your two hands and go like this, and naturally they'll want to go up and form a mountain. So that's the best way to think of that. And now, Sarah, just getting back to the question that I just skipped over by accident, Sarah from Radnor, PA says, I'm wondering about a hot spot thought to be causing the East African Rift. Is there any consensus on whether there's one hot spot, two, or more? Thank you. And so I'm not going to dive too deep into this because I think later on we're going to have somebody actually give a talk on mantle plumes. But just as a primer, there are geochemical evidence that these are separate plumes. So maybe one big plume originating deep in Earth and then spreading out. And I'm going to leave that until we have our mantle plume talk. Why don't mountain ranges keep growing higher and higher? So again, let's think about two pieces of crust moving together and forming a continent, and then pushing up into a mountain range. And you have to think eventually, as we keep pushing the mountain up, well, there's going to be other forces acting on it, right? So we're going to be actively eroding and weathering those mountains down. Even as we push it up, there's still processes working to bring mountains down and erode them away. So even though the Himalayas are still currently being uplifted, right? They're still going up, still raising. There are these different processes going on at Earth to wear them down, and eventually, the forces that are pushing these plates together and forming the mountains will no longer exist, because maybe there'll be a change in forces. It's like what happened on the East Coast. We have Pangea Assemble and the Appalachian Mountains. And then we start breaking apart Pangea, and the forces that created those mountains just aren't there anymore. And they turn and they want to split the continent apart.